Imagine the heat radiating directly through the soles of your boots. The smoke around you is so thick, it feels like a physical weight.
Oh yeah, it's completely suffocation.
Right. And the noise of the burning timber is just absolutely deafening. You are standing outside a residential fire, and you have exactly 4 minutes and 40 seconds.
Which is no time at all.
Literally none. You have under 5 minutes to completely change the toxic 1,000-degree atmosphere inside that structure. Oh, and here's the catch.
There's always a catch.
Always. You cannot use any mechanical equipment.
Wow.
Yeah. No giant gas-powered fans, no exhaust systems. You have to save the lives inside using nothing but a window, the weather, and, well, your mastery of physics.
It sounds like an impossible physics puzzle, doesn't it?
It really does.
I mean, it's like trying to drain a swimming pool with a straw while sort of just standing there holding a stopwatch.
Yeah.
But, this is the reality of the fire ground.
And that is exactly the mission for today's deep dive. Welcome, everyone. We are looking at a really fascinating piece of source material today.
Yeah, it's incredibly detailed.
It's an actual state examiner's practical exam guide for firefighters. And the specific procedure we're looking at is called horizontal natural tactical ventilation.
It's quite a mouthful.
It is. But we are going to unpack the high-stakes science of fireground airflow. We'll look at how first responders literally harness the forces of nature to save lives.
And it is so heavily regulated.
Okay, let's unpack this because it absolutely blew my mind that something as seemingly simple as opening a window is actually this rigorously graded, high-pressure, life-or-death operation.
What's fascinating here is that the procedure isn't just about breaking glass.
Right.
Or, forcing a door open.
Right.
That is a really common misconception. It is actually about treating the burning building like a living, breathing system.
A respiratory system, basically.
Exactly. The state examiner isn't grading a firefighter's ability to swing an axe. They are grading their ability to manipulate a structure's respiratory system.
Which is wild to think about.
It is, because the primary objective is to alter the internal climate. You're drastically improving visibility, dropping interior temperatures, and removing highly toxic products of combustion.
All to support the life safety of the trapped occupants, right?
Yeah.
And the interior fire attack.
Precisely.
And what struck me immediately in the examiner's guide is that, well, before a single piece of glass is broken, before a window is even touched, there is this massive mental checklist.
Oh, absolutely. And the candidate actually has to vocalize these prerequisites out loud to the examiner.
Right. You can't just run up to the house and act. You have to prove you are prepared for the absolute worst case scenario.
Yeah, you have to talk through it.
It honestly reminded me of a pilot running through a complex pre-flight checklist for a commercial airplane, except the runway is currently on fire.
That is a perfect analogy.
Yeah.
The examiner requires the candidate to announce several strict safety prerequisites before that 4-minute and 40-second timer even begins.
So the clock hasn't even started yet.
Nope. You have to loudly declare that you are fully geared up in personal protective equipment, or PPE.
Oh, okay.
You have to state that you've located a secondary means of egress, basically pre-planning your emergency escape route in case the structure begins to collapse.
Because things can go south instantly.
Exactly. Then you must confirm the shutdown of utilities to eliminate secondary hazards.
Like what? Like a gas leak?
Yeah, like a ruptured gas line fueling the fire. Or live electrical wires shocking the crew if they're standing in water.
Wow, yeah.
And crucially, you must declare that you are continuously monitoring for an IDLH environment.
Okay, wait, I have to pause you right there on IDLH.
Sure.
Because that acronym is heavily emphasized all over the source material. What exactly does it stand for? And physically, what does it mean for the firefighter on the ground?
So IDLH stands for immediately dangerous to life and health.
Okay.
It is the critical threshold where the environment literally becomes lethal. We aren't just talking about a smoky room here.
Right, it's not just coughing a little bit.
No, not at all. An IDLH atmosphere is so toxic, so oxygen deficient, or just so superheated that a single unprotected breath could cause immediate irreversible lung damage or death.
Just one breath? That is terrifying.
It is. The smoke at a modern fire is filled with carbon monoxide, hydrogen cyanide from all the burning synthetic plastics in our homes, and unburned fuel gases.
Wow.
So if the environment hits that IDLH threshold, the firefighter must explicitly state they are going on air.
Meaning they are pulling their mask down and utilizing their SCBA.
Right, their self-contained breathing apparatus.
They are sealing themselves off from the outside world and relying entirely on that tank of clean, compressed air on their back.
Exactly. You're transitioning from breathing the ambient air to being completely self-reliant on a very limited air supply.
Okay, so the pre-flight checklist is done. You are in your gear, you have your escape route, your air is on.
You're ready to go.
But then, looking at the guide, the very first action item isn't breaking a window, it's confirming authorization with the incident commander, the IC.
Step 1.
But wait, I have to push back on this logic.
Go for it.
If your entire job is to let the deadly smoke out of the building to help the people inside, why delay? Why stop to ask for permission on a radio? Doesn't literally every single second count?
Every second absolutely counts, yes. But a poorly timed second can be catastrophic.
Really?
Yeah, the source material emphasizes this heavily. Uncoordinated ventilation does not put a fire out. It can actually intensify the fire conditions.
How so? I mean, it seems like getting the heat out would always be a good thing.
Well, it comes down to understanding what a modern fire needs to survive. Most residential fires become ventilation limited very quickly.
Meaning they run out of air.
Exactly. They consume the available oxygen in the room and start to smolder. This produces massive amounts of dense, dark smoke.
Which is bad.
It's very bad because that smoke is essentially unburned fuel just waiting for a spark. Or, more accurately, waiting for oxygen.
Oh, I see where this is going.
Yeah. So if the interior attack crews, the firefighters inside the building with the hoses, are trying to locate the seat of the fire, and you certainly introduce a massive rush of fresh oxygen from the outside.
By busting open a window.
Right. You could trigger a flashover.
Okay, I've heard that term in movies, but what is the actual mechanism of a flashover?
A flashover is a thermal event where every combustible surface in a room ignites almost simultaneously.
Everything all at once?
Yes. The heat from the fire radiates down from the ceiling, baking the furniture, the carpet, the walls. They start to off-gas flammable vapors.
Oh, wow.
They are right on the verge of erupting, but they lack oxygen. If you break that window uncoordinated, fresh air rushes in, provides the missing oxygen, and the entire room goes from a localized fire to a completely engulfed inferno in seconds.
That is insane. So you could pull the fire directly onto your own team inside.
So you aren't just feeding the beast, you are actually giving it a steering wheel. You are directing the fire toward the fresh air. Worse than giving it a steering wheel, you are creating a high-speed highway directly to your crew.
Yikes.
The fire will travel instantly along the flow path of that fresh oxygen. That is why the incident commander is looking at the entire chessboard.
They need to see the big picture.
Exactly. They ensure the ventilation supports the overall incident action plan and happens only when the interior hose lines are charged with water and ready to absorb that energy.
Got it.
So the candidate has to vocalize this coordination. They say something like, Command Ventilation Group, confirming authorization to perform horizontal natural ventilation on the Alpha Bravo side.
Wait, let me stop you there. Alpha Bravo, I assume that's fire speak for the sides of the building.
Good catch. Yes, in the fire service, to avoid confusion, buildings are labeled by letters.
Okay, how does that work?
The front of the building, usually the street-facing side with the main entrance, is side Alpha. Then you just go clockwise.
So the left side is Bravo.
Right. The rear is Charlie, and the right side is Delta. So the Alpha Bravo corner is the front left corner of the structure.
That makes a lot of sense. It completely eliminates any ambiguity when someone on a radio says the front window versus the side window.
Exactly. When you're in an emergency, you can't afford confusion.
Right. You have to make sure your move isn't going to accidentally take out your own pieces on the board.
Precisely.
So the IC has given the green light. The interior team is ready with the water. Now we transition from the command structure to the actual forces of nature.
This is where the physics really kicks in.
The guide requires the candidate to analyze the ambient weather. You have to identify the windward side, where the wind is hitting the building and entering, and the leeward side.
Which is the opposite side where the wind naturally exits.
Right. And here's where it gets really interesting. Because the underlying concept here is something everyone listening has probably experienced.
Oh, for sure.
It's exactly like when you are trying to set up a cross breeze in a stuffy apartment during the peak of summer. You know, you open the front door, you open the back window, and you try to get the air flowing to cool the place down.
It is the exact same fluid dynamics principle, just scaled up to a lethal environment.
Right, a slightly higher stakes apartment.
Slightly. Instead of trying to cool down your living room so you can comfortably watch TV, you're trying to strategically push out toxic airborne contaminants and 1,000-degree gases while the walls are burning around you.
It's mind-blowing.
And knowing the wind direction dictates the entire airflow path through the structure. If you get the windward and leeward sides confused, the physics will violently work against you.
Because if the wind is blowing at 15 miles an hour against the front door, and I just intuitively kick the front door open because it's closest to me, I'm doing it wrong.
If you do that, you'll likely trap the crew inside.
Oh, wow.
Yeah. Instead of the smoke naturally venting out, that 15-mile-an-hour wind will pressurize the building. It acts like a plunger.
Pushing it all inward.
Right. Forcing the superheated fire gases deeper into the structure, directly onto the interior attack crew we just talked about protecting.
That is brutal.
The examiner will fail you immediately if you do not properly identify how the ambient weather is going to interact with the structure's openings.
All right, so we've mapped the weather. We know which way the wind is blowing. Now we finally get to manipulate the building.
Now the tools come out.
If I'm standing there with my tools, what is my very first physical move to get that smoke out without pulling the fire toward me?
It's very specific.
The guide lays out a very specific and frankly non-intuitive sequence. You start on the leeward side, the side shielded from the wind, and you have to create an opening at the highest possible point.
Yes, the high exhaust.
I literally had to read that twice. Why do I start on the exit side and why specifically go for the highest point?
It comes down to basic thermodynamics. Heat, smoke, and fire gases expand and they naturally rise.
Right, hot air rises.
Exactly. They pool at the ceiling and build tremendous downward pressure. By going to the leeward side, the side of the building where the wind is naturally pulling air away,
creating a low pressure zone.
yes, you open the highest point and you are creating a chimney effect.
Okay, chimney effect. So the high pressure inside desperately wants to escape to the low pressure outside.
Exactly. The guide lists upper story windows, high wall vents, or transom windows as prime targets for this.
A transom window, like those small horizontal windows you sometimes see sitting right above a door frame.
That's right. Because they are situated so high up on the wall, they are absolutely perfect for this.
Well, that makes sense.
By opening these specific high points first, on the downwind side, you are giving the deadliest, most superheated gases a place to escape without introducing a massive rush of turbulent air.
So it's a controlled release.
Yes, it bleeds off the pressure inside the building, immediately improves visibility for the interior crews, and starts dropping the interior temperature before you ever introduce the fresh, oxygen-rich air.
You are basically popping the pressure relief valve on a boiler.
That's a great way to put it.
But then the guide points out a massive pitfall. Once that high window is open, you have to completely remove hidden obstructions.
Yes, step 4.
It was completely mind-blowing to me that ordinary, everyday household items can literally halt life-saving airflow.
People don't realize it.
The guide explicitly mentions things like curtains, drapes, plastic security coverings, or window screens. The examiner will aggressively deduct points if you shatter the glass but leave a simple mesh bug screen in the frame.
They absolutely will.
How can a flimsy little piece of mesh ruin a tactical ventilation? It's mostly holes.
It absolutely can ruin it, and it's a trap many candidates fall into. It seems totally trivial, but a standard window screen can reduce airflow by up to 50%.
50% from just tiny little wires.
Yes, 50%.
Yeah.
And that's all because of fluid dynamics.
Okay, break that down for me.
Air behaves like a fluid. When you push a fluid through a mesh screen, it doesn't just flow cleanly through the holes like you'd think. No. The air molecules drag against every single tiny wire in that mesh, creating what's called a boundary layer.
Boundary layer.
Okay, it causes massive friction and microturbulence right at the opening. In a natural horizontal ventilation scenario, remember, you don't have a high-powered mechanical fan forcing the air through.
Right, you're just using the weather.
Exactly. You are relying entirely on passive pressure differences.
So that friction from the screen just acts like a brick wall to the smoke.
Precisely. Any obstruction, a drawn blind, a heavy drape hanging down, a security screen acts as a dam. It just traps the heat.
Wow.
So the firefighter has to physically rip those obstructions out of the frame using a pike pole or their hand tools. The candidate has to loudly tell the examiner, I would completely remove curtains, blinds, and screens to maximize the opening and allow unrestricted airflow.
I love that detail because it paints such a vivid picture. You aren't just opening a window, you are clearing the throat of the building so it can finally exhale. So the high exhaust on the leeward side is completely open and cleared of screens. Now, what about the replacement air? Doesn't nature abhor a vacuum?
It does. And if we connect this to the bigger picture, this is the exact moment the entire respiratory system of the structure activates.
Okay.
You've created the high exhaust, dropping the pressure. Now you move to the windward side, the side the wind is actively hitting.
The front door, usually.
Often, yes. The procedure mandates opening the lowest available point on this side. This means ground level windows, front doors, or lower side doors.
Which creates a fascinating physical mechanism. The way I visualized it from the source material was almost like pouring cold water into a bathtub full of hot water.
Oh, interesting.
Yeah, because the fresh air from the outside is significantly cooler and denser than the 1,000-degree toxic smoke inside.
That's a great way to visualize it, because the fresh outside air is cooler and denser. It naturally wants to stay low to the floor.
Right.
When you open that low windward inlet, the wind drives that fresh air inside. It literally acts like a physical ram.
A ram, wow.
It slides in underneath the superheated thermal layer, and it physically pushes the heat and toxic smoke up and toward that high leeward exhaust you already created.
It's a beautifully elegant system.
It really is.
You are entirely replacing the contaminated air, creating a full flow path without ever plugging in a cord or starting a gas generator. The wind pushes the fresh air in low, the dense air forces the hot smoke up, and the building naturally purges itself.
It really is elegant.
Yeah.
But it is vital to remember that a fire ground is an incredibly dynamic environment.
Things change.
Fast. The vents are open, the air is flowing, and the smoke is clearing, but the 4-minute and 40-second test is not over.
You can't just walk away.
No. This raises an important question. How do you keep the crew safe once that massive flow path is actually established?
Because, as we established earlier, you've essentially just given the fire a massive gulp of fresh oxygen. Even if it's coordinated with the hose team, it's still oxygen rushing through the house.
Exactly. Which is why the examiner's guide mandates constant ongoing vigilance.
Yeah.
The candidate must explicitly state that they are continuously monitoring for changing fire conditions and structural stability. You have to watch for a fire extension.
Meaning the fire traveling somewhere it wasn't before.
Yes. Did the new powerful airflow accidentally push the fire into a hidden wall cavity?
Oh, wow.
Or draw it up into the attic space? You have to be watching the eaves and the roof line constantly.
That makes sense.
Furthermore, weather is notoriously unpredictable. Wind conditions can change in an instant. A sudden shift in wind direction can completely reverse the flow path.
Oh, man. So if the wind shifts 180 degrees, what was a safe inlet suddenly becomes an exhaust.
And it becomes a blast furnace of exiting superheated gases.
That is terrifying.
If an interior crew was advancing along what they thought was the cool inlet path, a wind shift can suddenly bathe them in lethal heat, potentially trapping them.
That is truly terrifying to think about. You meticulously set up this perfect cross breeze, accounting for thermodynamics and fluid dynamics, and a sudden gust of wind flips the script entirely.
In seconds.
It really highlights why the communication aspect, the constant radio traffic with the incident commander and the interior teams, is graded just as heavily as knowing which specific window to smash.
It is a delicate balance. Every single step, from the PPE checks, to the wind analysis, to the high-low execution, to ripping out the bug screens and the ongoing monitoring, it's all a mandatory, non-negotiable component of the state exam. If you miss a step or do it out of sequence, you fail.
Harsh but fair.
Because in the real world, missing a step when you are manipulating a building's airflow costs lives.
So what does this all mean? When you look at this 4-minute and 40-second practical exam, it proves that in the world of firefighting, air is just as powerful a tool and just as dangerous a weapon as a hose full of water.
Absolutely.
It completely reframes how you look at the buildings around you. Next time you accidentally burn dinner in the kitchen and the smoke alarm starts blaring, you are going to intuitively understand the invisible physics at play.
You'll know exactly what to do.
Right. You'll know to quickly find the wind direction outside, open a low window on that side to let the dense fresh air act as a ram, and open a high window on the opposite side to let the heat and smoke naturally escape.
And you'll also remember to pull the screens out of the window frames if you want to get the smell out 50% faster.
Exactly. Take the screens out. But looking at this deep dive leaves you with a really fascinating, almost unsettling thought to mull over.
What's that?
Well, the entire strategy we've unpacked today relies on natural airflow, relatively drafty spaces, and easily removable obstructions like flimsy screens and curtains.
Right.
But think about the evolution of modern home design. We are moving rapidly toward ultra-sealed, heavily insulated, profoundly energy-efficient structures.
Oh, that's true. With the thick double or triple pane windows.
Practically unbreakable windows. Consider how this evolution in architecture might be fundamentally changing the way our buildings breathe.
They don't breathe anymore.
Exactly. As we make our homes incredibly efficient at trapping air to save on our energy bills, we are radically complicating the very physics that firefighters rely on.
We're sealing the boxes up too tight.
It makes you wonder how this architectural shift will force first responders to completely change the way they fight fires in the future.